Yeah, is it visible? The slides is,
Yes, sir.
yeah. So this is about the carrier statistics. So far, we have qualitatively understood the things what is happening. We have seen the entrance. We have started with the important thing was we have seen that conductivity is one important parameter of the material, and which decides its electrical characteristics. And this conductivity depends on the carrier concentration. One of the factors is the carrier concentration. So, in order to find out the carrier concentration, we have invoked the energy band structures, etc. So, we have some. Now we are in a position to quantify it, the carrier concentration, whether it is intrinsic or whether it is doped. Because we have seen two types of semiconductors. One is intrinsic semiconductors, and then other one is the extrinsic semiconductors. So we have seen in general from the energy band structures and the statistical law, or the distribution function, we have seen that the carrier concentration is decided by the integration of density of states multiplied by the probability function. It could be Fermi function or Max simplified to Maxwell's Boltzmann distribution law. So integrate product of this integrated over the different energy ranges can give us the carrier concentration. That is one thing. So with that, we can write down this equation. Before that, just this I want last class I could not give this. Actually, these are the typical energies required in extrinsic semiconductor. We have seen that the donors will be requiring certain amount of energy, or donors and acceptors. So you can see that phosphorus in silicon, the energy required is 0.044 electron volt. Then arsenic, it is 0.049. Then these are the uh, typical ionization energies for the dopants. Actually, similarly for germanium, similarly for p-type, we can see that this. So this will come in the band diagram very close to the. In the case of n-type semiconductors, it will come very close to the conduction band, and p-type it will come very close to the valence band. So this anyway, going back. So with that thing for the intrinsic semiconductors, this is the expression Ni, the intrinsic carrier concentration. Nc stands for the density of states in the conduction band, and then this is the probability function. This is actually Fermi function approximated to Maxwell's Boltzmann distribution, because we are considering an like a non-degenerate case where the large density of states are available in the uh, conduction band. So this is Ni. Similarly, for intrinsic whole concentration, Nv is the density of states in the valence band, and then this is the probability function. And then we have seen that the product will be this, and this is a constant because it depends on the Eg, and it will be dependent only on temperature. So we have this is one important relation we have to keep it in mind. This is known as the law of mass action. Now, one thing we have to understand, all we are here, all these cases we are talking of the equilibrium carrier concentration actually, or like whether it is on the intrinsic case or whether it is extrinsic case. For me, distribution gives the equilibrium carrier concentration. Very often, we will be seeing that later on when we deal with the devices, etc. We will be invoking a non-equilibrium case also, where the carrier concentration changes, that is, it deviates from the equilibrium value. So those cases we will discuss of very often of a quasi-Fermi state. That is, it is not in quasi-Fermi means it is not in equilibrium state. So very often we discuss a Fermi energy or Fermi function for the non-equilibrium condition also. So you talk of a Fermi function there also. But as Fermi function, as we understand, it is discussed mainly for the equilibrium, thermal equilibrium condition. So this is then for intrinsic carrier, intrinsic case, this is the expression. And for doped, not see very important, non-degenerate silicon or non-degenerate semiconductor, the electron concentration is given by EF. This is the Fermi energy. EI is the intrinsic Fermi energy. And then for a whole concentration, it is Ni EI minus EF by kT. So again, we'll get this. So one thing we have to keep it in mind is the law of mass action, whether it is intrinsic or extrinsic, we assume that it is valid, and both the cases, the product of electron and hole concentration is constant. That is why when we increase the electron concentration, correspondingly there will be a decrease in the hole concentration. Similarly, when we increase the hole concentration, there will be a decrease in the electron concentration, so that the product remain constant. So whether it is intrinsic or extrinsic, the product remains constant. Now, if find out the carrier concentration. So this is the starting point. So this is nothing. It's a very simple thing. This is about we are taking an extrinsic semiconductor where you have mobile carriers and immobile carriers, or you have Nd is the donor atoms and Na is the acceptor atoms per unit volume, and P is the whole concentration and N is the electron concentration per unit volume, of course. So this we can safely say that charge neutrality exists. So here we are assuming that when we say Nd, we are assuming whatever impurities we have added, they are all ionized. Because we have seen that the ionization energy is very small. So at room temperature, all these donors and acceptors will be ionized. So they are not, even though we are adding them as neutral atoms, within this they will be ionized. So it donors will add to the positive charge, acceptors will add to the negative charge, and holes will be having positive charge, electrons will be having negative charge. So overall, the charge neutrality will be maintained. So this is our basic equation. Very often we'll be using this law of mass action plus this will give you the whole of your carrier statistics is around this actually. So we can consider three cases where intrinsic already we have seen Na, both there is no doping there, so it is a the equilibrium concentration, thermal equilibrium, carrier concentration can be considered, and then we can talk of one-sided, heavily doped one side. So one side could be degenerate, and then we have the symmetric doping where Na as well as Nd is significant. So these are the three situations one can talk of. So in the intrinsic case, we have seen that both electron and hole concentration will be same, and we can use that equation which I have shown in the beginning for that finding out the Ni. So using this, substituting the values in this, we can, I'll leave it as an exercise. Equilibrium concentration, if Na and Nd dopants are present, then the electron concentration will be given by. Are you familiar with this equation? Have you come across this equation? This N and P equation? Hello?
Yes. Yes, sir.
Have you seen this equation?
Yes, sir.
Where?
In first semester, sir. Don't
Yeah,
remember.
normally we don't deal with this equation actually, because we will be assuming that in, for example, so that is what we are discussing here. Because normally, if you put this, for example, if you consider this in the n type, if you consider the n type, nd value will be much greater than na. So you can neglect the na contribution in this. So, and na, it also will be much greater than na also. So this will be, what will be equal to? What will be n then? If na is very small and na as well as uh, nia is very small, then what will happen to this equation? Hmm?
ND by 2 plus
So
ND
nd
square
by
by
2 and plus nd by 2. So what is it?
MD.
It's nd actually. So one can see that if it is for an n type, electron concentration will be nearly equal to nd. It is, of course, there is an approximation involved, so it is approximately equal to nd. You agree to that? Hello.
yes sir.
Yeah. So if because the practical value, if you take the practical value, Ni is typically around 10 raised to 10, and doping densities are of the order of 15 and above. See, for example, 10 raised to 50, 14 to 15, to that is lightly doped, then it can go up to 10 raised to 20. You can see around the 5 to 10 orders of difference between Ni and doping. So one can safely assume that Ni is much less than Nd. Then if you are considering an N-type dopant, Na can be neglected. So that way, N will be, the electron concentration will be equal to or nearly equal to Nd. Similarly, for a P-type, this is the equation that the same, using the same argument. One can find out if doping density is high as compared to the Ni, then we can say that the whole concentration will be nearly equal to Na. So we will see that in the most of the standard textbooks, we will see that the electron concentration is in if we are talking about the extrinsic semiconductor, the electron concentration will be taken to be equal to the donor density, and in the case of a p-type material, it is taken to be equal to the acceptor concentration. So this is a very important relation. Whereas, strictly speaking, it is not true, because there is a thermal equilibrium. Intrinsic area concentration is also there. So the full, if cases where you are see, for example, so you can work out some examples. You can see that suppose it is kind of uh, compensated n type. Compensated n type means you have acceptor atoms are also there, but it is nd is dominating, but it is not very high. So that means a is also there, na is also there, and then if it is lightly doped, so then we cannot ignore the contribution of ni in those cases. So you have to see the situation. Suppose in a given problem, uh, if you see that, yeah, there is a significant Na is present, and it is, if it is lightly doped, then for finding out the electron concentration, we need to use this equation. It's a quadratic equation. Actually, if you can work it out and see that it is a quadratic equation, and solution for n will come in this form. So otherwise, but fortunately, most of the time we can assume that the electron concentration is equal to Nd, and similarly for hole concentration, it is P is equal to Na. And since N into P is Ni squared, even for extrinsic semiconductor, so P will be in a N-type semiconductor, P will be equal to Ni squared by Nd. And in the case of p-type semiconductor, the electron concentration will be Na squared by Na. So for an n-type or p-type semiconductor, you can find out the majority carrier and minority carrier concentration. Majority carrier concentration will be decided by the dopant concentration, and the minority carrier concentration is decided by Na squared divided by the dopant concentration. So that way you can find out the majority and minority carrier concentration in the given device or in the given material. So this is was a very important relation. But if you want the exact value, you may have to use this relation. So if it is heavily doped, so this kind of equations are used. This is what we were discussing. So you can see that n is equal to nd, p is equal to ni squared by nd, and for acceptor concentration much higher than nd, then and then it is much higher than ni. But we are assuming there are two things we are assuming here. One is it is non-degenerate. Second thing is it is all impurities are ionized. This is a very safe assumption that at room temperature the impurities, whether it is n-type or p-type, all of them are ionized. So we can say that p is given by this, n is given by this for the n-type. So this is what I was telling. N is equal to for n-type the electron concentration is approximately equal to the donor impurity concentration, and the whole concentration will be approximately equal to Ni squared by Nd. Similarly, for p-type material, where acceptor concentration is much higher than Nd and Ni, then we can talk of the whole concentration will be approximately equal to Na, and the electron concentration will be approximately equal to Na squared by n. Any confusion there?
No, sir.
It's okay now. This is very important, actually. Unfortunately, you may not have done this experiment. Otherwise, I could have asked you this. So, how many of you have done that energy? Any of you could do it in the second semester? That energy gap experiment, band gap measurement through conductivity measurement. Any of you could do it in the second semester?
No, sir.
Nobody has done. So that was a very interesting experiment. You will see that actually what you, I mean, I just briefly elaborate you because that is a very important experiment. You will be studying about it in your third semester, that characterization paper, you will be studying about it. Like you will see that in that experiment, what you are doing is you are measuring the conductivity versus temperature. We will be discussing actually the conductivity versus temperature. We can see that actually. I will qualitatively discuss today. I don't have the graph, but you can see that. But let us start with absolute zero. At 0 degree Kelvin, all your valence band is fully filled, and your donors are not, or your impurities are not ionized because they don't have energy at 0 degree Kelvin, because you have seen that certain amount of energy is required to ionize them, to liberate electrons or holes. So that way your impurities are all unionized, they are not ionized. So that means your conductivity will be very small. As you increase the temperature, gradually the impurities start ionize. The donors will start giving electrons to the conduction band, and acceptor impurities will start giving holes to the valence band. So gradually you will be seeing an increase in the conductivity. So that region is known as the extrinsic extrinsic region of the conductivity temperature characteristics, because that region is dominated by the extrinsics or impurities. So impurity dominated, you can say. When all the impurities are ionized, then the intrinsic contribution comes. So at room temperature and above, you will see that the carrier concentration will be increasing, and that will be the intrinsic regions. So normally we will see that even though you will be using an extrinsic material, you will see that the conductivity and the band gap is measured, because you will take it to intrinsic region. So you have uh, two separate region. One is in the conductivity temperature graph. You have two region. One is the extrinsic conductivity region. Other one is the intrinsic. So you will be taking your graph to intrinsic region, and there you do the calculation. It's not that so that is very important when you do the experimentation. So this the conductivity varies with the temperature because of that. So that is a very important result. So you can see it in any of your textbooks. Probably I may not have provided the slide, but we can see that. You should see that actually. Yeah. Now, determination of Fermi level. This is again, you can find out where the Fermi level, using the same earlier equation which I mentioned. Using that, we can find out the position of the Fermi level. So the EA is the intrinsic Fermi level, that is close to the middle. For the n-type material, it will be decided by this nd by ni, a log of natural log. So you can get that. Similarly, for uh, p-type material, the position of a Fermi level is uh, this given by this kt natural log na by ni. And, so this kind of thing. So this will be, we will see that later on. We will be using this when we discuss about the PN junction, etc. So one interesting, because I'll try to give you some numericals on this. You can see that when you increase the donor density, this your Fermi level will be going, the gap will be increasing, and it will approach towards the conduction band for the n-type material. And similarly, this gap will increase, and it will, the Fermi level will be going towards the valence band. So that you can see that you can take up typical values of nd and na and change it. See, for example, you can consider for first for 10 raised to 15, then you consider for 10 raised to 18, 20, because these are the typical values of dopant densities we use. So then you will see that the Fermi level will be shifting towards the conduction band or the valence band, depending upon n-type or p-type. So that is a very interesting result one can see. So this is one worked out example I have just mentioned here. So this is actually we are taking a silicon sample doped with 10 raised to 17 arsenic atoms per, and whole concentration. You are supposed to find out this and Fermi level, and Ni is given. So you can take advantage of the relationship we have talked of. So since Nd is much, so N naught is taken to be Nd, so that doping density is given. Then we know that this is given. You can find out using this, the whole density you can find out. N naught is Nd, so you can Ni squared by this you can get. Then I can take advantage of this. N naught is Ni into this. So from this I can go for the Ef minus Ei, because I know N naught, I know Ni. Ni is given in my problem, so I can find out the Ef minus Ei. So this, that way I can find out the position, the difference between Ef and Ei is given. So I know where is Ei. Ei will be in the middle, so I know the where is Ef. So that is what we will see in the next slide. You can see that Ef will be 0.407 away from EI. So if you go on increasing the doping density, you will see that this EF will be moving closer and closer to EC. So this is one example. You can see that you can change the the doping density and see that how it shifts. Similarly for P-type also. Yeah. So this was the first thing I wanted to discuss today. Any questions? Hello.
No, sir.
So now what I'm going to do is I will take my assignments, and then today's session will end with the question paper, previous question paper. So that's what I'll.
So, is
Yeah,
there any use of degenerate semiconductor?
degenerate semiconductor. Actually, as such, there is the heavy doping because it they degenerate. But very often, say for example, when you make ohmic contact, so ohmic contact you have n plus, so it is nearly it's a degenerate semiconductor. Then your emitter region, it's heavily doped. So some of the effects of degeneracy comes in. Then very often in your lasers and semiconductor lasers and LEDs, you want a large injection. When you study about the p-n junction, it will become clear. So very often what will happen is you are unintentionally you are going, because there are other advantages of heavy doping. So so you will be approaching almost a degenerate condition, but otherwise it is not good for as far as the semiconductor material, because the material property is changing. There is a shift in the band gap, because the band gap will decrease, so the intrinsic carrier concentration will increase. All sort of problems are there. But very often what happens is, for two examples I can tell you is, one is the ohmic contact. When you make the ohmic contact, there is a heavy doping, so there are some consequences of that there. Then you have this emitter region of the BJT, where heavy doping is there. Then third one, of course, is the LEDs. So there, this kind of situation comes. So when your calculations, we have to uh, worry about effect of degeneracy there. Otherwise, normally, I mean, if you ask me whether it's a good thing, because our all calculations are going to be in trouble actually, because we very often what we do two three things actually. One thing is, we assume that even though strictly speaking we have to use Fermi-Dirac statistics for the distribution of carriers, we very often approximate it to the Maxwell. So almost all textbooks, the calculation is based on Maxwell's distribution law. So we so that is going to change if there is, and we are assuming that the Fermi level is within the forbidden band. So all those things will, and if it is a degenerate case, it can go into the conduction band or valence band. So these consequences will be there. So it is not an appreciable thing as far as the semiconductor device operation is concerned. But why we, then you may ask why we are discussing it? Because of this reason, because some cases where we approach degeneracy. Is it okay?
Yes, sir. Yes, sir.
Yeah.
Got it.
Yeah. So now I want to discuss some of the questions I gave you earlier. So I want to see whether somebody could, or what I'm trying to do is, I'll see that any of you have done. Uh, if it is already done by you, then I will, I'll be happy. So otherwise, I'll give you some hint in doing this, some, so that some direction. Uh, so because I want, are you able to see?
Yes, sir.
Yeah. So because I want you also be getting involved in this, not that every time I do. Yeah, this was one problem. This, how many of you have tried this microprocessor example? Nidhi, of course, have done it. What about others? Yes, anybody?
This is of first assignment, now, sir.
Yeah.
Yes, sir. Tried.
Why? What was the problem? Difficulty?
So I think the value is going too much.
So what?
That's why.
That is
So
what is expected. Well, that is what the crux of the matter is, that actually, you, of course, you should use proper units. That is okay. But the crux of the matter is, value will go. Nidhi, both of you, I will. I suggest, because I am not going to work out these problems here. So if what I am trying to do is, if somebody has done it, it's fine. They will discuss with. They will help the others also to work it out and see the importance of this. Second thing is, I will give you some direction in which you can work it out. Actually, so the value. See, actually, why I gave you this problem. Did you understand? I'm asking Bhaskar. Already I have
I
discussed
think,
with
sir,
the
that
yeah. Hmm.
physically, it is not possible to take lots of transistor at the same
Yeah.
time.
That was the importance. This was to impress upon you the importance of microelectronics. You could have never made a microprocessor without microchips or microelectronics, because if you are only using discrete transistors, forget about vacuum tubes, even the transistors, if you are using discrete transistors, you could have never made a processor. Because today, why I have taken the example of microprocessor, because you know that today when we talk of IT revolution or electronic control or whatever, microprocessor is the basic brain of everything. Everything is all this uh, computation or all this intelligence, giving intelligence to the system, whether it is AI or whatever. uh, Giving intelligence to the system is through the microprocessor. All of you agree to that, or any objection to my that statement?
So agreed.
The intelligence is given by the microprocessor or microcontroller, actually, because the computational thing. So that only thing is we are increasing its capability, so that was made possible by microelectronics. So that is why the very first lecture, because I had like Bhaskar was telling why then everybody is going after computer science and all those things. uh, but without a microprocessor, none of these systems will work, that I can tell you. Anyway, so we will see that the numbers coming will be immense, actually. So that's all. So that is expected anyway. So it will we will be seeing that the power consumption will go into kilowatts, the size will be quite large, the weight will be quite large. That is expected. So that, don't worry about that. Of course, I assume that the proper units are considered, so it should not be a mistake through because of the units you are considered. That's all. Otherwise, the numbers are expected to be high. Yeah. So you can do it.
Yes, sir.
Yeah. Try to do it and see, and you can work, do it among yourself. You help others to do it. Probably Farah may not have done. Niti has already done. So Niti and Bhaskar help Farah also to do it, and others also, if they are interested, you can help. So I'm just dividing my work with you people. Yeah. So this is one thing, that is an interesting problem I could find about the importance of microelectronics. And now, have you tried this? So this was, I think, probably from my second lecture. I don't remember which lecture, but so this is. Have you tried this? Any of you? So the first question is, why wafers are circular in shape? Have you noticed this? That
Yes, sir.
wafers, yeah, why it is circular?
Sir, that process, because of that process, spin
Which process?
or something.
Pardon?
Sir, I'm forgetting the name. That spin, sir.
Ah, chokra, ja. See, yeah, Bhaskar, do you know that? And Farah?
So no, sir. No, sir. Sorry.
See, actually, the most widely used process for making your silicon ingot or silicon monocrystalline ingot is Chokrasis technique or CZ technique. There you will see that pulling is there. You have a solid liquid solution, malt is there, then molten solution of silicon, polysilicon is there, then you have a seed crystal, and then you pull. This pulling process will give you this circular shape of the wafer. What is the shape of your chips generally? Chips. Is it also circular?
No, sir.
Yeah. What is the shape?
Rectangle.
It's a rectangle. Yeah, it is
Square
not.
rectangular.
Yeah, it's not square very often. It can be rectangle. It can be square also, but never circular actually, because edges and all those things will come. But wafers are, that is the difference. The wafers are circular because of the you can say that the pulling process, because the crystal growth, that pulling process gives the wafers the circular shape. Whereas the chips, because depending upon chip size is not standardized now. Earlier days, the chip size was standardized. It was 1 millimeter by 1 millimeter square. But nowadays, because you have a system on chip, so depending upon the application, because for example, you have SoC chips of a cell phone will be different from SoC chip of your tablet or a digital camera. So the sizes are not fixed actually, because the packing density, the number of blocks in that are different. So it can be rectangular. Early days it was 1 mm by 1 mm kind of stuff, actually squares. But now increasingly it could be rectangular and things like that. And the sizes are also not fixed. So that is basically the wafers are circular because of the pulling process, crystal growth process. Then this is effective mass of electrons, which is higher, electrons or holes?
So holes,
Yeah. Why?
because they are less mobile comparison.
Yeah, but it is, yeah. Why they are less? Actually, it is opposite. They are less mobile because they have a higher mass. See, for example, a truck and a car, the mobility actually, because for the same amount of energy you supply, the truck will be moving less, or the mobility of the truck will be less because its mass is higher. So the mobility is not the other way around. You got my point. The mobility
Yes,
comes
sir. Yes,
from,
sir.
yeah. So you cannot say that its mobility is less, so that is why it is having a high
Because of
effective.
high mass.
It
Yes,
is
sir.
high effective mass. Why then? My question is, why it has a high effective mass then?
Because it has a high mass.
Or why it is having a high mass? That is the question, no?
Because it is. mm, just-
Yeah, yeah. Nidhi, any answer?
No, sir.
See, actually, we have to understand what is effective mass. Effective mass was coming because of the internal forces acting on the electrons. In both cases, it is electron motion only. Whether it is a hole or whether it is electrons, it is the motion of electrons. But there is a fundamental difference in the electron motion and the hole motion. Electrons are moving freely, whereas holes motion means electron motion from one bound state to another bound state. It is not a free motion. It is going from one bound state. It is bound from one state to another bound state. It is going, so leaving behind a vacancy. That is what the whole motion is. So the internal, see, the effective mass gives you an idea about the internal forces acting. That is how we have introduced the effective mass. So the internal force acting on holes will be more, and again we can simply see that it is going from a bound state to another bound state. Naturally the forces acting on them will be more, so the effective mass of the holes are more, so naturally the other things follow. So that is why holes have a higher effective mass, because their whole motion is motion of electrons from one bound state to another bound state. So the internal forces acting will be more, and effective mass is deciding the internal forces acting on the carrier. That is why. Got it?
Yes, sir.
Yes, sir.
Yeah. So now this, I think we have discussed the knowledge of mechanical and chemical properties of silicon. Yeah. Like any, do you remember why you want to know? Because electric, as far as electronics is concerned, knowledge of mechanical, sorry, electrical properties are fine. But then why sometimes we are interested in the mechanical and chemical properties of silicon?
Some mechanical because in MEMS device we
Yeah.
have.
Yeah. I think we did have a discussion about this chemical properties because of the chemical processes we are following, like etching and all those things. I think I remember we have discussed this. Anybody has any confusion here?
No, sir.
So now the next question: difference between silicon and silicon. This was one of my all-time favorite question. So it looks
Sir, silicon is
same.
a polymer.
Yeah, it's a hydrocarbon actually. Like you have used the vacuum pump in your some experiment with the ground floor. There is a So that oil used in the diffusion pump, it is silicon oil actually. It's a hydrocarbon. Basically, that oil is made of this it is popularly known as silicon oil actually, whereas the silicon is our favorite boy, that is material. So there is a big difference. One is a hydrocarbon, the compound, and it doesn't show any of the properties of semiconductor anyway. So that you should not be confused about that. And this question, do you know about this? Because we have discussed about the orientation, and we have discussed about the how to identify the different orientations and all those things from the wafer side. So, but do you think that the wafers used for bipolar and MOS technology is same or different?
So I think for most technology we use 111 orientation.
No, it's other way around. One zero
So sorry,
zero.
we don't use the 111 because of the
Yeah,
positive
yeah.
carriers introduced in
Yeah,
that.
atomic density. Whereas bipolar
Yes.
technology, that actually this was one of the thing which delayed the starting of the MOS technology, because actually the bipolar transistors were very quite popular, and there they were using 111 orientation, and because of the processing and chemical processing was easy, and all those other issues were there. I mean, that basically because of the processing is. Whereas when they started making most devices with the same orientation, see, we will see later on, we talk of surface state. That means at the surface there is a discontinuity. So that we physics we talk of surface states. So in 111, the surface state density is much more, and MOS being a surface device, the surface state density can severely affect its performance. So whereas 100 have the less surface states. So anyway, more about it when we discuss about MOS devices. That time we will
So
discuss more
I
about it.
think some unwanted carrier has generated because of the defects and all of
No,
that.
that is a surface state actually. Surface state, what happens is they can capture the carriers, so they will cause leakage current, etc. They can absorb I mean, capture the carriers or atoms from the surroundings, and all those things happens actually. So the surface
Yes, sir.
immediate problem is of surface state actually. So that we will discuss anyway in more detail later on when we discuss about the surface state and things like that. But important thing we have to remember is the orientation of the wafer used for bipolar and MOS are different. One case we used 111, and other case 100. Yeah. So this was the first lecture. So I recommend that you write down these answers and keep it with you, so that you remember. Uh, and if you want, you can post it to me also. But at least I expect that you try to briefly you try to answer these questions. Yeah, this have you tried? This was from second or third. Have you tried this question? First question.
No, sir. Sorry.
Nidhi, have you tried?
No,
Yeah, after the first assignment, you thought that, oh, nobody is doing, why should I do? No, that was the problem.
no, sir.
No, because first one you did, and after that you thought, oh, nobody is doing. So see, now at least I have 1 point compared to others. So now it's okay. I don't have to do the second one. That's what. So can you suggest a way to do this? Like, who will take the charge of doing this? Do you understand the this numerical? What are the things given? Can you you are able to read? No.
Yes, sir.
Yes, sir.
Yeah. How will you do this problem? Actually, why I'm say, giving numericals and the problems is this in our type of teaching methodology. We don't work out problems or discuss the problems. We take certain topics and finish it off, and later on we don't apply it, because engineering is all about applying our knowledge in practical or solving a lot of numericals and the things like that. So that habit you need to develop. So, and in our exams also, these questions may not be asked in your MSc exams, but that's not, we have to look beyond MSc, passing MSc exam also. Yeah, that's why I have put this question. So now let us try to see, and then you can do it yourself later on. Let us see what are the things given. One thing we can see is the green, the light is green, that is wavelength is given. What from that, what kind of information you can get? Wavelength is given. So what is the information you are getting from that? Yes. From wavelength, what can you find out? Anything? Can you find out anything from wavelength?
Velocity.
What is the use of velocity?
So frequency.
Frequency, sir.
Frequency. What is the use of frequency? What is the use of frequency? So wavelength is given. What is the velocity? Let me ask you, what is the velocity?
H by lambda.
Sir, yeah.
Hc by lambda.
What is the velocity? Hmm? Any idea about the velocity? So you said that velocity can be found. How will you find out the velocity? Wavelength is given. How will you find out the velocity? Come on. Hello?
Yes, sir.
Yeah. What is the velocity? Now let me ask you, what is the energy? Can I find out the energy from this wavelength is given? Can I find out the energy of the photons from the wavelength?
Sir, equals to h nu.
Where is nu?
News.
Nu is not there. Only wavelength is given. Can you find out nu? H nu is the formula for energy, but suppose you don't know but the wavelength is given.
C by
Then
lambda.
C by
what,
C by lambda.
what is C by lambda? What is C by lambda? Dimensionally, what is C by lambda?
Sir,
So
nu is
light
equals to
velocity
equivalent.
by
Nu.
wavelength.
Velocity by wavelength. What is it actually? C by lambda.
Sir, it's nu.
It's new actually. It's
Yes,
frequency.
sir.
So
Yes, sir.
if you want to find out the energy from this, is you can use, because wavelength into frequency is constant, that is velocity. So if you know the velocity, then you can find out the energy from wavelength, that is hc by lambda. So because why I am using c? What is c?
C
Speed of
velocity of
light.
light 3
Light velocity.
It's the velocity of light. H is Planck's constant, so I can find out the energy of the photon.
Photons.
Now this is one thing. So one thing I can find out is the energy of the photon. Now what is thing? What is other thing given? It is the power. Light of 100 microwatt. Watt means, what is given? What is it? Watt represents?
Power.
What is
power, sir.
power? Is there any relationship between power and energy? Because you are finding out energy and you are finding out the
dw.
E by
Change of energy. dw by dt.
dw by dt. What does it mean? It is the energy by time per,
Time, yes, sir.
yeah.
Power.
So from this, how can I find out the number of photons? Actually, power is this we have to understand. Actually, you will be using it in your optoelectronics paper also, because there you are developing detector. That is why I selected this problem. In the third semester, you can, this kind of problems are asked even in your net or gate exams also, where photo detectors will come into picture. The power is basically, other way of writing the power is number of photons into energy of one photon per, that is number of photons per second multiplied by the energy of one photon will give you the power. So from this you can find out the number of photons, because power is given, energy of one photon is given. You got it, the question answer?
Yes, sir.
See,
Got it. Got it.
power is number of photons striking the surface per second into energy of one photon.
One photo.
So
Got it.
yeah, so from that you can find out the number of photons. Got it? Because power is given, then energy is given. Energy you can find h, of course you have to hc, you have to put the value. We can, these are standards available, so you can find out the number of photons from that. So will you do that?
Yes, sir.
Yes, sir.
And now you can see, actually now what I'm doing is simply changing the wavelength. So again, the energy can be found out, and then the power, in order to keep the power same, how many more photons you have to add. So again, you can do the same formula one can use and find out the number of photons. Okay, so this you will do.
Yes, sir.
So we had the next question. We had a lot of discussion on this. So will the electron and hole effective mass of this we have discussed earlier. So I'm not discussing this. So this again today we have discussed using law of mass action, obtained a position of intrinsic Fermi level or in an undoped semiconductor. You have to do this numerical. Numerically, you have to prove that numerical means you have to prove this, that intrinsic Fermi level. You have to prove that it is near to the center, and what are the kind of conclusions you draw, and that you have to do that. So the equations which I have given you today, you can use that. I assume that you will be doing it. This actually I have worked out, so I am not showing you that. Later on we'll take. Now, this, have you tried this? No, I don't think after the first assignment, you have not tried any of the other questions, it seems. No? Any of you have done this question? Hello?
No, sir.
So I think I will leave it to you to do it again. I will give you one more opportunity. So today we will take the third part, because quickly we will take the third part of our discussion. So this is, anyway, you have to do this numericals, or this 1-2 numericals. It's very simple actually. There is not much involved, provided you understand the basics actually. What is the force? How will you calculate the force applied by an electric field? What is the how will you calculate?
F equal to QE.
Yeah, that's all. Then you can find out its momentum, and then you can find out that yeah, those details. You second one also similar kind of thing. Straightforward. These are all straightforward application of the equations only. Not only thing is you need to understand the basic concept, basic relationship. That's all. Your high school knowledge will help you if you know that equations. Again, electric field is given. You have to find out the velocity, and then you can take compare it with the thermal velocity of the carriers. Again, you have to thermal velocity. You can look into any book on semiconductors. You can find out the thermal velocity, and then you can make the comparison between the drift velocity and the thermal velocity. This is I expect that you do this. This so I'll next thing I'll do is I'll take that old question paper quickly, because there is, and I just want to see what was there in the. Let me know. Are you able to read this? Screen is visible?
Yes, sir.
Yes,
Yes, sir,
sir.
visible.
Yeah. So let us see the first two questions actually. It's a compulsory question. The question is, uh, conductivity of an insulator is insensitive to temperature. Explain. I think we have discussed sufficient. So you can answer this. Anybody has any difficulty in answering this question? So you'll write down the answers to this question. Hello. Hello.
Yes, sir.
You will be able to do this. Answer this question.
Yes, sir.
So what about others? Niti and
Yes, sir.
yeah. You are able to read the question. No, the conductivity of an insulator is insensitive to temperature. Explain. That was a question asked. I don't know which year this question is. It is EL12 actually. So it is a relatively recent question paper, probably last to last year's question paper. Yeah. Okay. So you are supposed to write down, and if you don't are not able to, you have to tell me. Otherwise, you are supposed to write down and get it checked either by one among you take the. I mean, why Bhaskar will take care of that. That make sure that people do it, and if you have any confusion, you can get back to me and discuss. The second question, again, we have discussed it sufficiently. Effective mass of electron and holes are different in a given material, and why? Yeah,
Yes, sir.
it can be answers can be written.
Yes, sir.
So this also you try, because very often I find that people will say that they know it, but then when they write, they make mistakes. So what I suggest is you discuss among yourself and find an answer, and see that your answer. And in case of any confusion, you get back to me. Either you write to me or we'll discuss separately. So these are the two questions from the compulsory part. Then let me take up the unit one questions actually quickly. Is it visible? The unit one. Forget about the other part. Is it visible?
Yes,
Are you
Yes,
sir.
able to?
sir.
Yes,
Yeah,
sir.
are you able to? You are able to read? No, it's no. The quality is not very good, but then this is all I could actually. Thanks to Naveen, this is all I could get. Yeah. So, what is the origin of energy bands in crystalline solids? On the basis of energy band, explain the temperature variation of electrical conductivity in semiconductors. So, and I think you will be able to do work it out. So you try to answer this question, write down the answers. Don't hesitate in writing the answers. So it's very important, because very often we think that we know the answers, but when we write, so this is one of the mistakes many of you commit actually, that when you write down the answer, because subjective numericals and subjective papers, like especially when you have difficulties, when concepts are involved, then it is better, even though it a bit tedious part, but one need to write down the answers and see and get it checked, so that you are sure of that what you are written is right actually. Because very often when we discuss, you feel that okay, I know it, but when you write, you make mistakes actually. So please write down these answers and get it checked. Yeah. And then this is second is a numerical which we have done, in the sense you can find out, show that it is the EK diagram, the slope will decide the effective mass. So can you do this second one also? Yes. Hello.
Yes, sir.
We can try. I think I have a write-up of this.
Pardon?
We can try.
It is there in, you can refer my notes actually. There we have one slide which is discussed also, or you can refer the textbook Streetman. That derivation is given, so you can show. Actually, you start with actually what is done is you write down first. If I remember well, you start with energy is written in terms of momentum,
Yes, a
and
momentum
then
half mv square.
yeah,
Yes, sir.
then instead of mass you write down the effective mass, that is all, and then you write h squared k squared, that by 2m and all those things will come. And then you will see that you have to take the differential and things like that. So if in case of any difficulty, I mean, this is this kind of questions can be repeated. So better do it. Either you go through my notes or textbook. And if both the cases it is not working, and if you have any difficulty in, it is straightforward actually. I don't find any. If you get the that right relationship, you will be able to do that. In case of any difficulty, you can come back to me. We'll solve it actually, because I take this, not my assignment, but these assignments or these question papers will be taking seriously, because many times the questions can be repeated, so we'll take it seriously. So this is other one. This we again we have discussed the difference between Maxwell's distribution and Fermi-Dirac distribution of carriers. So we have to show that Maxwell's distribution can be, because first you write down Maxwell's and Boltzmann's distribution, and then see that, show that under certain conditions we can approximate Fermi-Dirac distribution to Maxwell distribution. So we very often we will be using Maxwell, so that that we can do that. So this also you try to do that. So in case of any difficulty, we'll have another, because again, all these things are discussed in the notes. So if you refer the notes or the book, it may not be there. This question may not have been discussed directly in the book. So you textbook may not be, but in the slides, I think we have mentioned this, so you can see the slide actually. Actually, the difference between the Maxwell's, Boltzmann, and Fermi-Dirac is that one plus will not be there. Actually, that one, actually, that is an essential difference. So, so that we have to keep it in mind. As far as the mathematical expressions are concerned, one is the Maxwell's equation is exponential minus EF by E by EF by KT, whereas Fermi function is one plus same thing actually. So with non-degenerate, that one can be negative when E is much large. You can see that one can be neglected. So that way it will go back to Maxwell's distribution and things like that. Say here, if somebody wants, they can write the time permits. They can write what is the origin of Fermi-Dirac distribution. Or Fermi-Dirac distribution comes because of the Pauli's exclusion, involvement of Pauli's exclusion principle. So that points also can be written. So then again, what do you understand by doping of semiconductors? What is its utility? So again, I think it is we have discussed. We have spent sufficient amount of time so that you are able to answer this question. Then with a neat diagram, energy band diagram of intrinsic semiconductor, silicon doped with N type and silicon doped with P type. any change in the band diagram if it is heavily doped. So this also, I think we should be able to do it. If you are not able
Heavily
to,
doped
heavily
means,
doped means it will go, the Fermi level, see the important difference is the Fermi level will go into the conduction band
conduction
or
band.
valence band. Yeah, yeah. P-type, it is P-type, so it both cases, both N-type and P-type. One case it will go to conduction band or very close to the conduction band, and other case it will go to valence band. That's heavily doped means that degenerate. Yeah, this explain the role of mobility we have discussed. So this you can refer the notes and then write down your answers. So that is, and then hot carrier effect and velocity saturation of carriers. This again we have spent one lecture on that, so you should be able to write down this. So I'm not expecting that all of a sudden you will be able to answer, but then you have to refer back because these are subjective type of questions. So you need to refer back and your notes, and then you write down the answers to this. You can do that. So this that covers the unit 1. So again, there was one more question. I think I won't be able to display it here. There is one more question from unit 1. Okay, it is there. This, of course, we have not discussed the Hall effect, so that I can do. So this, I expect that you try to work out these questions and the work out the other problems I have given. So that gives it more effective, and I will also feel happy. I will be also encouraged to or motivated to add more questions, because that will be interesting for me also to look out for good practical examples. So that will help me also. So you have to show some response from your side, then only, otherwise we will get just like your normal class, we can continue talking about this and we can finish. So that should not happen. You have to proactively get involved. Okay.
Yes,
Yes,
sir.
sir.
Thank you, sir.
Yes, sir.
Okay.